All right, welcome everyone to 1.6. In this video, we're going to be calculating limits using limit laws. And I'm splitting up 1.6 into kind of three different cases, right? So this case one is going to be the easiest case. It's going to be when your limits kind of yield 0 over a non-zero. That's what I'm using n to stand for. So 0 over non-zero or non-zero over non-zero, right? And the claim is this is the easiest case that we have. So we're going to develop some limit laws and use them. And then actually we're going to upgrade those and get ourselves something called the direct substitution property. And this is going to be able to help us evaluate some of these limits very quickly. Okay, so let's go over some of these things, the limit laws. So we're going to suppose that we have a nice constant c and that we know that the limits of f and g exist as x approaches a. In this case, the claim is for limit laws, basically all of your dreams come true. That kind of all of the properties that you would hope hold true do hold true. So for instance, if you want to figure then the limit as the sum of f plus g as x approaches a, well, that's going to be the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So you just figure out these limits individually. Again, we know they exist. Add those together and you get the limit of the sum. Okay, so like I said, more or less, all of your dreams come true. The things that you would hope would be true actually are. So pause the video for 2 seconds here and try to guess then, maybe 2 through 5. I want to know, what do you think these will evaluate out to? So again, pause the video. I'll come back here in just 2 seconds and spoil the surprise. All right, and here they are. Number 2 says that if you have constants, you can factor them out of the limits, right? So it's just the constants more or less along for the ride. Constant times whatever this limit of f of x is as x approaches a. Number 3 says that you can go ahead and distribute limits across multiplication. So you can kind of distribute them across addition up here, number 1. Number 3 says you can distribute them across multiplication as well. So if you can figure out what the limit of f is, the limit of g is, well then you multiply those together. And that's going to be the same as the limit of f and g being multiplied together. Likewise, number 4 says you can distribute limits across division. So you can just put a limit up here in the top and the bottom, and there you go. Again, kind of provided that you're not dividing by 0, right? We don't want to allow for that. And for number 5 here, the limit as x approaches a of some constant. Remember, c is a constant value. Think of it like 5 or 2 or negative 10, something like this. And so as x approaches a, the constant says, who cares? I'm a constant. I don't care what x is doing. I'm going to be my constant, whatever 2, 5, negative 10, right? Okay, so there's those limit laws. Let's continue on. As x approaches a, well, what's the limit as for x as x approaches a? Well, x is approaching a, so therefore it's going to approach a. Likewise, we can kind of upgrade this, right? So if you have powers of x's, right? So x to the n, then as you would probably expect, this is going to be, oh, my computer's going a little bit crazy on me. There we go. A to the n, right? We're basically just plugging in an a everywhere we see an x. And finally, maybe the most complicated scenario, if you don't just have x to the n, but if you have some function raised to an nth power, right? And again, you're taking the limit as x approaches a, then indeed this is going to be the limit as x approaches a of f of x. Remember, this actually exists, and we take all of that and we raise it to the n power. And this says, when appropriate, which basically means, right, we can have all sorts of powers like square roots, right? And if this happened to be a negative value, then it wouldn't make any sense, right? It doesn't make sense to take the square root of a negative value, at least not in this class. Okay, so let's move on to an example. I would like to evaluate out this limit given all of our limit laws. So some of you who have seen calculus before, you will know how to do this very, very quickly. We're going to break it down kind of step by step for this one example, and then I promise we'll speed it up. Okay, so in this case, because we kind of have this division going on, I'm kind of thinking maybe my first step would be I would like to write the limit as x approaches 0 of 2x squared minus x divided by the limit as x approaches 0 of 3 plus x. So I'm going to go ahead and distribute my limit to both the numerator and the denominator. I'm allowed to do that because of good old number 4 there, right? Number 4 says I'm allowed to do this. Okay, now I can see that I have some addition and subtraction, stuff like this. I'm going to go ahead and write this next as the limit as x goes to 0 of 2x squared minus the limit as x goes to 0 of x divided by the limit as x goes to 0 of 3 plus the limit as x goes to 0 of x. Right, so I'm going to distribute the limit across addition and subtraction in this case. Right? So again, using these limit laws. Next up, well, some of these can be evaluated already. Right? So in fact, some of these, let me go ahead and evaluate them. For instance, this one right here, the limit as x goes to 0 of x, well, that we have a limit law for, right? That's number 6. So as x goes to 0, what does x go to? Right? Well, 0. There we are. Likewise, here in the denominator, the limit as x goes to 0 of x, that again is going to be 0. What about the limit as x goes to 0 of 3? Well, it's a constant, right? It's 3. It says I have nothing to do with x. Leave me out of it. That's just going to be good old 3. The only one that's left is this one, and actually we need to do one more step here. I'm going to go ahead and take this 2 and factor it out. So I'm going to do 2 times the limit as x goes to 0 of x squared. We can do this because of this constant multiple rule here, right? Number 2 says that you can factor out these constants. And now the limit as x goes to 0 of x squared, well, that's going to be good old number 7 here, right? Where n is 2. I have an x squared in this case. So in this case, I'm going to get 0 squared. So this is 2, 0 squared minus 0 over 3 plus 0. I'll simplify that down to just 3. So I have 0 on top and 3 on bottom. That's my answer. Well, you usually would simplify this, right? And a 0 divided by anything is going to be really 0. Okay, so that's how we can apply these limit laws to figure out limits. Not quickly, but we'll do quickly here in just 1 second, right? So we have something called the direct substitution property, and this is what makes it very fast for us, right? So if f is a polynomial or a rational or root function, and a is in the domain of f, then we have the limit as x approaches a of our function, f of x, is equal to just f of a, saying that we can just directly substitute in an a everywhere we see an x. So for a lot of functions, we can just plug it in. So if I was to do this back for our function up here, right, this is a rational function. It's a polynomial over a polynomial. So this applies, right? So if f is a polynomial or a rational function, for instance. So if I just was to plug in 0 everywhere I saw an x, notice what I'd get. I'd get 2 times 0 squared minus 0 over 3 plus 0, which would give me 0 over 3, which would happen to be 0. Right? So this limit would evaluate out to 0. This is much faster, right? So this direct substitution property makes life really great. So notice this was one of these cases where I had 0 in the numerator and something non-zero in the denominator. In this case, right, it was 3. Right? So that's, again, we're in this first case. 0 on top, non-zero on bottom. These limits we like. Let's do one more example here. So the limit as x goes to negative 3, and notice we have a root function, we have a polynomial, right? So kind of, we're going to try this direct substitution property. What happens if I just plug in negative 3 everywhere I see an x? So if I try plugging it in, I'll have the square root of 1 minus negative 3 divided by negative 3 squared. Well, negative 3 times negative 3 will be 9. Minus 4 times negative 3. So I'm going to have the square root of 4 divided by 9 plus 12. That's going to give me 2 divided by 21. And that is my answer. So let me really quick state this remark, right? This is a great theorem, and this is really the easiest case. So kind of when we go to evaluate out a limit, the first thing we're going to do is try plugging in a everywhere there is an x. This is going to help us determine which case we're in. Right now we've really only seen one of these three cases that I'll bring up over 1.6, this section. So we've dealt with the cases where you have 0 divided by n, and then we just saw one where you had n divided by n. Right? So we had 2 divided by 21, some non-zero divided by another non-zero. Okay. One more thing that you sometimes see every once in a while, these sometimes make great multiple choice questions. Problems like this, again, this we're going to apply the limit laws to, right? So we have some function. We don't really know a lot about it except for as x gets closer to 2, the function gets close to 3, right? So the limit is 3. And likewise, g, we don't know a lot of information except for as x approaches 2, the function g approaches -2. And we'd like to figure out this complicated limit, so let's apply our limit laws here. I'm going to go ahead and write this as 5, the limit as x approaches 2 of f of x, minus, and so it looks like I have an x and a g of x. Luckily I can distribute limits across those, so x goes to 2 of x times the limit as x goes to 2 of g of x. Now luckily I know what the limit as x approaches 2 of f of x is, so I'm going to plug that in there. And I know the limit as x approaches 2 for g of x, so I'm going to go ahead and plug that in there. And that'll give me my final answer. So 5, and the limit as x approaches 2 of f of x is 3. Oh, I missed one, right? The limit as x approaches 2 of x. Well, that was the property, right? It says, again, we could basically just think of this as the direct substitution property. Plug in a 2 everywhere you see an x. Perfect. And then likewise for g, the limit here evaluates out to -2. So I have 15 plus 4 equals 19. And that's my final answer. All right, so that is the first case when you have either a non-zero divided by a non-zero or you have 0 divided by something non-zero. The second case, which I'll kind of combine into this video here, is a case we have already seen in 1.5. It's this case when you have a non-zero divided by 0, and this is going to yield a vertical asymptote, right? So the same claim as we've done this already. I'm going to do one more example here, and that's going to be the end of this video. So we're going to evaluate the limit as x goes to 1 from the right for this right here. So if I was to follow my technique now, if I plug in a 1, right? Let's try to use the direct substitution property and see what happens. I would get -4 on top, and if I plugged in 1, I would get 1 minus 1, we would get 0 on bottom. So again, this is a good indicator that we have a vertical asymptote, and this is the situation, some non-zero divided by 0. So really, we know our answer is going to be either positive or negative infinity. It's our job to figure out which. And so the question came down to, is this 0 in the denominator here just a little bit positive or a little bit negative, right? Because if you're dividing something really close to 0 but just a little bit positive, you know that this is going to be closer to, well, I guess with this -4 here, -4 divided by something positive would be closer to negative infinity. Likewise, if you have a negative divided by a negative, that's going to be positive. So if you have something really close to 0, just a little bit negative, we'd be going closer to positive infinity. Again, because a negative divided by a negative is positive. Okay, let me draw out my number line here. Here's 1. I'm approaching 1 from the right, so I'm going to choose a value close to 1, but just a little bit bigger than that. I'm going to choose maybe like 1.1 or something like this. And try plugging this into the denominator and see what happens here, right? So if I do 1 minus 1.1, I'm going to get -0.1. So this is really, really close to 0, but just a little bit negative. And notice this works if you were to choose, 1.01 or 1.001, right? In all of these cases, we know that if you plug in something that's bigger than 1 in for x, close to 1, but just a little bit bigger, that this is going to be smaller than 0, right? It's going to be just a little bit negative here. And so, because we have -4 divided by something very close to 0, but just a little bit negative, right? This negative divided by negative means we're going to get positive infinity. So this limit here, the limit as x approaches 1 from the right of -4 divided by 1 minus x is going to equal positive infinity. All right, that is the end for this video. It's really covered these two kind of subsections. One more to go. All right, I'll see you guys shortly.